Assalamualaikum warahmatullahi wabarakatuh. In this session, I would like to explain about moment distribution method, the effect of support settlement. Okay, the basic procedure to analyze beam using moment distribution method in considering or including support settlement. Okay, we look at one by one. Number one, we have to calculate member stiffness factor and joint stiffness factor. This is the main thing that we need to do in order to determine what we call as distribution factor. Okay, and distribution factor is actually member stiffness divided by joint stiffness, and we will use distribution factor in order to distribute member and moment. Okay, the next step is after we have determined the distribution factor using member stiffness as well as joint stiffness, we need to establish or we need to calculate fixed end moment. We need to calculate fixed end moment. Actually, support settlement. Okay, this support settlement is actually come from we can calculate fixed end moment due to support settlement. Means that FEM is actually come from two effects. Effect number one is actually come from the external loading, and effect number two come from support settlement. This is number one and this is number two. Okay, the next step after we have determined the fixed end moment due to external loading as well as support settlement, we will combine these two fixed end moment in one table. Okay, we will combine in one table and then we will start calculate the member and moment. Start with the first member and moment in the table, which is the fixed end moment. Okay, in the table, what we need to do is we have to distribute moment using this step. We have to calculate the member and moment by calculate the joint moment first. Joint moment is actually opposite with member and moment times with distribution factor. And then after that, the next step is we have to carry over moment. We have to carry over moment to opposite joint using the factor, using the carry over factor. And the factor is 0.5 for fixed end and 0 for pin or roller end. And after that, we will repeat the process again and again until the moment reaches 0. Okay, until the moment reaches 0. So total, lastly, we need to total all moment value from fixed end moment as the first member and moment in the table until the last moment in the table, and we total all the moment and we will get the member and moment for the beam. Okay, so let's look at example 3.1.4. This time we will discuss on the support settlement in beam. This is a continuous beam consists of two members A, B and C. Okay, actually we have done this example, but at that time we don't consider the settlement effect. Okay, this time we will use again the same beam by considering as well the support settlement in this beam. Okay, so let's look at the support settlement. Okay, support B settled by 25 mm downward direction. 25 mm downward direction. Okay, step number one, we need to calculate the stiffness factor. So we will use the same with the previous example, the same example without considering support settlement. So we have A and C. This is a DFAB, means at support. This is at support A. Support A is fixed, so the degree distribution factor is equal to 0. And at C, at support C, it is also fixed, so it is equal to 0. And the FBA plus the FBC, these two value, when we plus the FBA plus the FBC, this must be equal to 1 because this is actually DF at joint B. And distribution factor is actually equal to 1 except fixed n. Except fixed n. Okay, so we move to fixed n moment. Here is fixed n moment. Okay, fixed n moment. Okay, this is fixed n moment. Okay, due to external loading, we will get this. Okay, this one, and this one based on the given loading. And due to support settlement, what we need to do is we have to draw the settlement. So we will have support A, support B, and support C. Settlement occur at joint B as 25 mm. So this will be the delta 25 mm. So what we need to analyze here before we calculate the value is we have to study the behavior of this beam after settlement. For example, for member AB, this is B prime. For member AB, it rotates clockwise. Okay, from original, this one is original. Okay, this is original position. And this one is a new position. So what we need to understand is we need to measure the chord rotation. This is called as chord rotation. Okay, this is chord rotation, this one. Okay, and this angle or chord rotation, okay, we have to see the angle from the original position to the new position. We have to see the angle, how it rotates. So if it rotates clockwise, okay, it means that FEM must be negative because why? Fixed end moment is actually behavior. And one tips to remember the FEM sign easily is by looking at the angle of chord rotation. Because when angle is positive, FEM will be negative. It always opposite. This one must be opposite. Okay, so back to this. We go back to this. So we have to have, okay, the length of each member. So we will use the formula at 6 EI delta over L squared. Okay, over L squared. And please remember that since AB the rotation is positive, so we will get negative. This one must be negative. And for BC, the angle is negative. So the FEM must be positive. Because why? This is negative, and this one is positive. Okay, so FEM AB is what? It is negative 25, okay, minus 187.5, we get 25. negative 212.5 kilonewton meter. FEM AB, FEM BA. So this one is BA. FEM BA is positive 25 minus 187.5, and this is equal to 25 minus 187.5. We get negative 162.5 kilonewton. Okay, next is FEM BC. This is equal to BC. We have BC negative 15 plus 333.33. This is equal to negative or positive 318.33 kilonewton meter. This is moment. And lastly, FEM CB is positive 15 plus 333.33 is equal to 3. 15 plus 333.33, we get 348.33 kilonewton meter. Okay, so these are all the fixed end moment. Okay, both considering both effect, external loading as well as the support settlement. So means that after this we need to continue. Okay, we need to continue calculate fixed end moment. Sorry, not fixed end moment. Calculate not fixed end moment. We need to calculate end moment. End moment. Okay, in the table we have member AB, member BA, member BC, member CB. Okay, distribution factor, we have 0 here, 0 here, and the factor is 0.429. This is 0.429 and 0.571. Okay, the first member end moment in the table is come from the fixed end moment. Fixed end moment AB is negative 212.5, then negative 162.5, then 318.33, then 348.33. 348.33. Okay, this is the FEM. Okay, the first value is the first distribution. Okay, let's look at the distribution. Okay, distribution number 1. Okay, this is distribution number 1. Total moment means joint moment means BA plus BC. BA plus BC joint moment, it is negative 162.5 plus 318.33. Okay, we times with 0.429, so we will get negative 66.851. Okay, then we get the next value 318.33 minus 162.5 minus 66.851. This is 88, negative 0.979. Okay, next is carry over. The next value is carry over. We need to carry the value to opposite joint. Since both are pin, so it is 66.851 51 divided by 2, we get negative 33.426. And then 88.979 divided by 2. 88.979 divided by 2, we get negative 44.49. 449. Okay, and then next distribution. Remember to stop at distribution. So this one, there's no moment to distribute anymore. So this one is 0, 0, 0, 0. So we have to total all the moment. Total all the moments. Start from FEM. So negative 212.5 minus 33.426. So here we get negative 245.93. Okay, next, negative 162.5 minus 66.851. We get negative 229.35. And then 318.33 minus 88.979. We get positive 229.35. And the last value is 348.33 minus 44.49. So this is 303.84. Okay. So this is the value, the fixed, the member and moment for this beam, considering loading, external loading, as well as support settlement. So I want to continue to analyze this beam in order to draw the shear force diagram and bending moment diagram. So for the beam, okay, let's look at the beam back. Okay, fixed, roller fixed. Okay, for the bending moment diagram, we can draw directly. Okay, this is actually internal moment. And we can draw the bending moment diagram directly. Okay, so the sign that we have here in the table, this is positive, the sign, okay, representing the position, okay, of the moment in the diagram. Okay, so the first one is negative. So this is the first one, negative, as well as negative. And for the second member, it is positive, and positive. Okay, this is the position. The position means that the point of 245.93 is located somewhere here. The point for BA is located somewhere here. Okay, and the point for BC is located somewhere here, and the point for CB is located somewhere here. Okay, now to have the accurate, to have the salient point in the diagram, we need to have the shear force diagram. So from shear force diagram, so what we need to do this, because we want to estimate or calculate the salient point in the bending moment diagram for the beam. Okay, so we have to take out element by element. So this is number 1, AB, number 2, BC. Okay, number 1, AB. So here we will have like this. Okay, this is AY, this is BY, this is BY2, this is CY. Okay, then we have UDL here and point load if I'm not mistaken. Okay, point load at the middle, 50, 2 and 2. 50 kilonewton to meter to meter. Moment, the moment is negative 245.93. 245.93 as well as 229.35. 229.35. 229.35. So for AB, this one is AB. For AB, so by taking moment at A, is equal to 0. So it is negative 245.93 minus 229.35 plus 50 times 2 minus BY times 4. This is equal to 0. Okay, so we calculate BY value. It is negative 245.93 minus 229.35 plus 100. Okay, we divide by 4. So we get BY equal to negative 93.82 kilonewton. Okay, 93.82 kilonewton. Okay, since we have determined BY, so AY is equal to, AY is negative and negative, so it is 50 plus 93.82, we get 143.82 kilonewton. Okay, so this is for AB. For AB, so shear force diagram for AB will become this one. Okay, will become this. This is 50. BY is negative 93.82. This one is 143.82. So for the shear force diagram, we will get 143 going up like this, go straight, minus 50, go straight, minus 93.82. So this value is 143.82. Okay, and this value is 93.82. And both is positive. So this one is positive. So this is A, B, C. Okay, so for the bending moment diagram, okay, let's say we continue with BC first. Okay, for BC, we have positive and positive. Okay, here is positive and positive. This one is 229.35 and 303.84. 303.84. The UDL is 20 and 3. 20 and 3 meter. Okay, so this one is taking moment by taking moment at B is equal to 0. So it is positive 229.35. 35 plus 303 3.84, 303.84. It is 20 times 3 plus 20 times 3 times 1.5 minus CY times 3. CY times 3. This one is equal to 0. So it is 229.35 plus 303.84 plus 20 times 3 times 1.5 divided by 3. So CY equal to 207.73 kilonewton. So BY2. Okay, the previous one is BY1. This one is BY2. BY2 is equal to, this is equal to 20 times 3. 20 times 3 is 60. 60. So it is negative. So it is like this. So CY we get 207. This one is 207.73. 73. So we get 207.73 minus 20 times 3. Is it 20? Yes, 20 times 3. So we get 147. 147. Negative 147.73 kilonewton. Okay, so this one we draw the diagram. BY2 is negative 147.73. CY is 207.73. And UDL is 20. This is 20 kilonewton per meter. This one is 3 meter. Okay, so we draw the shear force diagram. So this one, okay, go down again like this and go up. So this one is 147.73 and this is 207.73 and this is negative at negative side. So this is shear force diagram for BC, and this one is AB. AB, okay, not ABC. This one is A and B only. So this one, okay, this one is A and B only. AB. Okay, AB. Okay, AB, this is the shear force diagram. Shear force diagram for AB. Shear force diagram for AB. Okay, and this one is shear force diagram for BC. Okay, when we want to draw the salient point in the bending moment diagram, so we have to draw BMD. Okay, we have to draw BMD. Okay, the first one just now for this one, this is the BMD actually. All this BMD. This is for the position BMD. Okay, how to do this? Okay, for BMD we do it for AB first. Okay, AB first, it is negative. Negative mean point at here, Okay, the first value, the first moment value is actually we get from the table. We get from the table, the value is negative 245.93. This is the value. Negative 245.93. Negative 245.93 and 229.35 and point load 50, point load 50. So from the diagram, from this diagram, from the shear force diagram, okay, we have to find the area of this. Okay, the area of this. Okay, the distance is about 2 meter, So we have to plus. Means that the first value in the diagram is negative 245.93. We have to plus the area. The area is 143.82 times with 2. So we get the next point. 41.71. 41.71. It is 41. Okay, this is negative side. This is positive side. Means 41 is located somewhere here. The value is 41.71. Okay, then the next point is we have to add 93.82 times 2. Times 93.82 times 2. So we get 229.35. It is positive. 229.35. So we get like this. Okay, check again. The value is 93.82 times 2. We get positive 229.35. We get positive. So here is the diagram. Okay, so this is the point. Okay, somewhere here. As well as this. The bending moment diagram. And for the second one, for C, this one is AB. For BC, we have here this one. The first value is it is positive. Positive means the value is somewhere here. It is 229.35. So it is 229.35 minus the area. It is 0.5 times 3 meter times 147.73 plus 207.73. So we get negative 303.84. So we get the value down here. This is 303.84. So the bending moment diagram for this one is only like this. Okay. So this is how we draw the bending moment diagram. Okay, from the shear force diagram. Okay, so that's all for this video. I will continue the next video insyaAllah later. Assalamualaikum warahmatullahi wabarakatuh.